So this presentation outlines my experience as an educator integrating interactive learning intervention into an advanced control course. So in particular, I will talk about how we implemented these interventions in live scripts submitted as homework assignments. So let me first introduce the class. It is a 6,000 level graduate course, MECI 6397, called Learning-Based Control. So the objective of this course is to illustrate how we can use data collected from a system, which is generally difficult to model from first principles, to obtain models and controllers and control laws. So topics cover a combination of system identification, machine learning, and adaptive control. So students are expected to be mathematically mature and have a knowledge about linear algebra, calculus, and probability, as well as have completed basic courses in controls and optimization. So my class typically has 15 to 20 students from our master's and PhD programs in mechanical and aerospace engineering and electrical engineering. So as for the course structure, I roughly divided the course into two parts. So the first, say, 2/3 of the class, weeks 1 to 10, are dedicated to face-to-face lectures. So I have 2 lectures per week, and each lecture is 75 to 90 minutes each. The remaining 1/3 of the class, so the last 5 weeks, are dedicated to a student-led project. So the course project really has the objective of putting class material into practice. And students are free to choose a project individually or to work in groups of 2. And for graduate research assistant, we really want to connect the project to their research. So in previous academic years, this is what I used to do. So I would introduce the lectures face-to-face for the theoretical concepts using a combination of PowerPoints and then the whiteboard. And then I would assign homework to practice on the theory of that week. And the homework were generally submitted in PDF, as you see here on the right. So this is one example, homework 5. The description is in paper format, let's say, even if the tasks included some computer-based problems, such as task 2. They had to open, for instance, in here, a Simulink model, and down in task 3, they had to inspect a MATLAB script. So I had iterate this format for a few years, and every year I would modify a little bit the content of the homework themselves by introducing more hints, more comment based on the student feedback that I was receiving. However, I had some problems with this approach coming from students. Students were complaining that they were not able to complete the homework assignments, either because they didn't have adequate background, sufficient computer skills for solving the assignments, or because they felt that the guidance provided in the paper format of the homework was not enough. And so they felt hindered in their solution. And as a result, the information retention was low, and this was also reflected into the execution of the other project. So I thought I had to do something here. And I started to look for best practices in student success, and I came across interactive learning. So interactive learning is a teaching and learning approach in which students are actively involved in the learning process through meaningful engagements, as opposed to passive reception of information. So interactive learning typically includes hands-on activity, the use of technology to promote the two-way communication and the real-time feedback. So interactive learning emphasizes the participation of the students, the critical thinking, and the active involvement to enhance the understanding. So the objective with this is to improve the understanding and the student success, enhance the retention of knowledge, and also boost the student experience. So once I found that I wanted to move into this direction of interactive learning, I reached out to MathWorks. And together with Melda and Armando here in this, hosting this webinar, we started to brainstorm ideas how to incorporate interactive learning into the curriculum and the lectures that I already had developed in the past few years. So keeping the same topics, but modifying the homework. So we identify 3 main guiding principles for our discussion. First of all, we wanted to build on best practices for student success. And I mentioned interactive learning earlier. Armando mentioned experiential learning based on projects. And the third aspect is asynchronous study. So students, especially after the pandemic, they became acquainted with accessing the material at their own pace whenever they feel they need a refresher. And so having a component of asynchronous study was important for us. The second point was to offer additional self-paced educational resources in the form of educational video, online tutorials, learning material, reading materials, and Armando already gave an overview of what MathWorks already has available and free for everyone to use. And the third aspect, we wanted to maintain academic rigor. So for us, that meant that the students had to implement the theoretical concepts on their own, concepts that they have seen in the lecture, in MATLAB programs, or in control systems from scratch using Simulink as well as MATLAB. And they also need to learn how to use the available algorithms in blocks from toolboxes in a responsible way. So the results is to use this MATLAB live script as a homework assignment. And this is what I'm going to talk about in the remainder of my presentation. So the result is a curriculum material, which we call Learning-Based Control with MATLAB and Simulink. It is freely available to download on MATLAB File Exchange. And it consists of the following live scripts. You see here the table of content. We have 1 live script per each module or topic that we covered in the lecture. So first off, homework 0, let's say, we offered some resources for preliminary work in the form of self-paced online courses on the basics of MATLAB, Simulink, and control design. So this module was not graded, and students were free to choose what they wanted to refresh or learn on these on-ramps based on their confidence level and the prerequisites. Now, let me show you how the brainstorming ideas were implemented in the live scripts. So I'll play this video. This is homework 3, in which we want the students to learn model reference adaptive control. Okay, so you can see, let me stop here. We teach in the first part how to design model reference adaptive systems based on the MATLAB, the MIT rule. And in the second part, we want to show them the Lyapunov rule. After the first introduction on model reference adaptive control, you see here we have references to the Simulink blocks and some reading material, TED Talks from MathWorks themselves that are linked. Then we go on to the homework itself, and you see how we first produce a summary of what we have seen in the lectures, so students can read through the theory as provided in my slides in class. And then they are asked, first of all, when the movie will play, to pick and choose blocks from a Simulink library that we created that pops up when they link to it, to recreate the same block diagram that they see in figure 2, okay? implemented the theory presented above. So the tasks that will follow will ask to modify some parameters in the implementation and create some simulations out of it. So I can move a little forward. So you see how the live script allows students to run several experiments, several trials, modifying the parameters of that Simulink model that they have implemented. This was the MIT rule. Second part is similar, again, with the link to the library that we had provided earlier to implement the Lyapunov rule, okay? And students, again, they had to run their simulations, modifying certain parameters and providing comments on what they have seen. So the first part was a feed-forward gain. Second part was a first-order system. You see how with MATLAB you can link to the formulas in the live script as well, promoting interactivity. As you see also here. So this fulfills the first two bullet points. So promoting interactivity, having best practices in student learning, and then maintaining academic rigor. The third part that we had in this homework, I move a little forward, was to use a shipping example provided by MathWorks. So here we have the quadroto control using model reference adaptive control, where the students had to use a block from the adaptive control library in MathWorks, reproducing a little bit the theory that we had introduced in class. So again, as before, we have the explanation of the concepts first, so we provide enough theory for them to work on, and then we ask them to use MATLAB and Simulink. Let me give another example. So this is homework 5, iterative learning control of the DC servo. Similar concept. In the first part, we introduce the topic. We provide a summary of what we want them to learn. And then in this case, because it's iterative learning control, the way that we have implemented the algorithms would, now that the Simulink model is going to show up. Yeah, you see. So we have a Simulink model that the students had to use, and then we ask them with these sliders to tune the given PID controller that was provided. And you see how MATLAB can plot in line. So it does the simulation and plot in line. And we ask them to implement an iterative learning controller on top of the PID to reduce some tracking error. And in this case, because we have several iterations that we have to run from the same Simulink model, we decided to run iteration and keep them for subsequent runs. And in the live script, you can plot it both in line and here on the right of the screen. So students could visualize as they run the simulation how the tracking error would reduce iteration after iteration. Okay. Similarly to the previous example, the last part of this homework also asked the students to use the iterative learning control block from the control design library in MathWorks. So this is, again, another shipping example that the student have to use. Okay, so this brings me to the summary of the curriculum development with MATLAB and Simulink for learning-based control that we have done using live scripts. So we prepared standalone modules for self-paced and asynchronous study. Each live script featured a concise yet informative description of the material and included tutorials, MATLAB tech talks, and other media type of material embedded in the text. Practice problems mirrored the theory and offered opportunities to write MATLAB programs, build their own Simulink models from scratch, use blocks from toolboxes that are already available from MathWorks, and execute shipping examples. And the set of questions that we could ask were very broad. We asked them to reflect on theory, observe the difference between simulations, observe the effect of user-defined parameters and initial conditions, and then test various algorithms to achieve the best performance. So this was the first 2/3 of my class. The second part of the curriculum was the class project. And students were expected to work on a problem using the tools that we see in the lectures for the duration of 5 weeks. So in this presentation today, I'm going to showcase 2 projects. And in the first one, we use reinforcement learning in an application to offshore oil and gas logistics. So here on the right, you can see the QR code for the GitHub repo. All the code is publicly available and you are free to use it. So the problem is the following. So we need to transfer crude oil from a platform that is typically positioned 300 kilometers offshore. And we need to do this at a regular interval, typically 6 to 8 days of production to maximize the operation. And this is done normally with dedicated shuttle tankers, which are called dynamic positioning systems. However, in addition to the large operational cost of these dedicated shuttle tankers, their availability is limited. We don't have so many DP3 capable vessels available globally. So our question was, can we use conventional oil tankers for this purpose and equip them with the advanced control systems for station keeping so that we can reduce the bottlenecks and also have more flexibility in our fleet? So we investigated the feasibility of replacing the DP3 with conventional tankers equipped with RL to maintain station keeping via rudder and propeller. So the figure here shows our setup. On the left, we have the oil platform here that we assume it's fixed. And on the right, we have the conventional oil tanker that is subjected to the ocean currents as it is not fixed. So the hawser connected the platform to the oil tanker is modeled as a rigid link. And here we have the offloading hose for the crude oil to be transferred. Now, the objective is for the controller to maintain heading and position by commanding the rudder and the propeller, overcoming the ocean currents. To describe the fishtailing phenomenon, we adopted a model which is available in the literature that you see reference here. So on the left, we have the hawser angle and the ship heading, as well as the tension of the hawser. And we consider an input current of 0.5 meters per second. Here you can see the simulation of the environmental and state variables from the paper referenced below. And on the right, you see how we implemented it in MATLAB. So we were quite happy with these results, and we assume our variables, the state variables, gamma, psi, and phi, and f, were accurate for our purposes. So for the kinematic and the dynamic modeling, we have three components. For the spread mooring systems with the rigid hawser, we consider one equilibrium point at nominal speed with zero lateral yaw velocity, meaning that the vessel travels aligned with the current. We linearize our model around this equilibrium point under the small angles, the heading angle and the current angle. For the ocean current-induced forces, again, we use a model presented in the literature, reference here below. And for the rudder and the propeller, the propulsion systems that allow the calculation of the lateral forces as a function of the starboard deflection and velocities, we consider force normal on each rudder section and the total lateral rudder force. Okay, we consider the station keeping under the fishtailing phenomenon as a Markov decision process. We consider states as 100 discrete positions depending on the ship angle, the hawser angle, and the sway direction. And we have postulated 10 discrete actions, okay, combining the steering direction, whether it was starboard or the port side. And we modulated this with 5 levels of thrust intensity. For 0% thrust, the system progresses cyclically and continues the natural fishtailing. The transition between states reflects, of course, the response of the vessels by comparing the applied force against the resistance of the current-induced sway and inertia. And we postulated the rewards designed to encourage proper suppression of the fishtailing. And of course, this was done by trial and error. So here you see a simulation results. I'm going to show you how the conventional tanker that you see on the left on our screen here is moving according to the ocean current that you see moving from right to left. And when we turn on the RL in a second, here you will see how slowly but surely the shuttle tankers reaches the equilibrium state and it is aligned to the platform. So the second project that I want to showcase is the use of iterative learning control for the trajectory tracking error reduction of a micro quadcopter. Again, here you have on the right the GitHub repository link, the QR code to the repo. So the background was a previous work from my lab, referenced here below, in which we considered a standard PID controller implemented for a trajectory tracking of satellite orbits. Okay, so we use the Crazyflie, the drone you see here on the right, as a surrogate for a satellite. Now, the PID that was implemented off the shelves was showing an offset, an error, probably due to the inaccuracies of the model. So on the left, you see position in the x-axis, on the left, and the y position, as well as the z and the yaw angle. So the only state variable that was tracking correctly was the yaw and even the altitude, the z position. And here on the right, you can see how the simulation from our model in green is far off from the reference in red. So we thought about enhancing trajectory tracking with iterative learning control in combination with the PID, mirroring homework 5 that I showed you earlier. So to reduce the tracking error in the pitch and on the roll axis, we implemented a heuristic ILC to reduce attitude reference and roll attitude reference error simultaneously, and manually tune the parameters. So here you see the formula that we use for iterative learning control, and on the bottom you see the simulation. So in red is the reference, The green is the original PID, and the blue is the tracking that we obtain after execution of the ILC. You see here the animation on the right. As we execute the repetition, the norm of the error decreases until we reach a reference tracking that we were satisfactory with. So once we have considered the pitch and the roll simultaneously, okay, let me run this animation. We validated it for the tracking of our orbital trajectory. So in blue is the original PID, the green is the PID with the iterative learning controller on the top, and the reference is the orbital trajectory in red. And you see how after the takeoff, it reaches the correct altitude, and then it follows the trajectory in the X and the Y, in pitch and roll. Okay. Now, after we had tuned our ILC, we perform a robustness analysis. So we suppose that we have some measurement noise in the position, which you see here on the left, and we want to verify how robust is the ILC. And we computed the norm of the error, simulated the drone, the Crazyflie, and validated the performances. And you see here, as I let the simulation run, that the ILC still is robust to the injection of some measurement noise, following our desired trajectory with, of course, more deviation, as in the case that was noise-free. So you see how also in this case, the implementation was successful and allowed the student to practice the ILC in a real project with a real hardware, although in simulation, and verify also the robustness to disturbances. And yeah, I let it play. Okay, so at the end of the course, we collected some informal student feedbacks in the form of answers to questions, reflections. So the first question was, in what ways did you benefit from using MATLAB live scripts from learning-based control? And here I report some representative quotes. The general theme was that using MATLAB live scripts gets you moving quickly, as it promotes intuition on learning-based control and provide more clarity on the method's impact. Some students liked how you could combine the code, output the plot, and have the explanation all in one place, because according to them, it made the learning process feel smoother. Some other students, as you see here in the last comment, felt that the pre-made scripts were a little bit push, run, and done. So they would have liked it the old way without interactivity. The second question was, what do you think were the biggest facilitators to learning using MATLAB live scripts as opposed to traditional programming environment? And the general theme was that MATLAB live scripts provides an organized document where all the figures are in line, the plots, so that the results can be analyzed right away. And as this first student said, plotting the results immediately can explain the concepts visually. Having space for both writing the notes and comments and codes and having all the live plots all at the same time, according to some students, was the best feature of the live scripts. What were the barriers? So we have seen good things about MATLAB LiveScript. What were the barriers that the students perceived? So here again, a general theme was that LiveScript can slow down the simulation a lot. And some perceive that understanding how the code interacts with the questions that they're given, so the empty space that we had to fill was difficult. Some were not familiar with Simscape model that we use for the shipping examples, but in general, having the regular M files was preferred in some cases. And in my experience, I don't know if it is because of habit that these students had seen the M scripts all throughout their career, as opposed to the live scripts, prompted them to perceive this as a barrier. And this last question, how could your instructor improve the MATLAB live script to make it easier to overcome these barriers? So one suggestion was to break down the live script, to have more simple concepts separated from the complex notions. And it would be helpful if the instructor provided a mix of live scripts for learning the basics and separate scripts of functions for more advanced or performance-heavy part, and live demonstrations in the classroom. Some students believe that doing it yourself is better than completing the code. And some general comments on the material and the experience. So generally positive comments. They perceive it as a great balance between theory and application, and they had the chance to apply the concept right away. Being able to do it from scratch was perceived as essential, so it was seen as a positive aspect. Some students suggest using simple and typical application examples before the more complex one. And combining practice with theory made a lot of the material simpler to understand. So this concludes my presentation. Here is, again, the QR code of the curriculum material with the link to MATLAB File Exchange.